Explain working of traveling wave fault relay. So when a short circuit or fault occurs on a transmission line, it causes a sudden massive change in the voltage and current at that specific point. This sudden change acts like a step function injection, creating high frequency electromagnetic transients known as the traveling waves. These waves consist of both voltage wave and a current wave, that is delta V and delta I. Once generated, these traveling waves propagate towards the outward from the fault location in both the directions along the transmission line toward the substation at either ends. They travel at nearly the speed of light, which is approximately 3 lakhs kilometers per second for overhead lines and slightly slower in the underground cables. These traveling wave relays are installed at the terminals, that is ends of the transmission line. Because these wave fronts are extremely steep and fast, the relays require specialized ultra-fast data acquisition systems. They sample in the incoming signal at the rates of 1 megahertz or higher, that is million of times per second, to capture the exact microsecond the wave arise. To make sense of the traveling waves, relays at both the ends of the line must be perfectly synchronized. They use high precision GPS clocks to place an exact microsecond time step on the very first wave front that arrives at their respective terminals. The most common method to locate the fault is by comparing the time difference of arrival, that is TDOA, of the waves at both the ends. If a fault occurs exactly in the middle of a line, the waves hit both the relays at the exact same time. If it happens closer to substation A, the wave hits substation A first, then substation B. The relay calculates the distance of a fault X from a substation A using the formula that we are using for the whirl loop or Murray loop type of equation. X is equals to L plus V into TA minus TB, that is time, into velocity. So it is the distance divided by 2, where L is the local line length or say total line length, V is the wave velocity, TA is the arrival time at substation A, TB is the arrival time at substation B. This method is incredibly accurate, often pinpointing a fault down to the exact transmission tower. The relay must determine if the fault is on its protected line, that is internal, or outside of it, that is external. It does this by analyzing the polarity, that is positive or negative sign of the initial voltage and current waves. By comparing the voltage wave against the current wave multiplied by the line's characteristic impedance ZC, the relay calculates the forward and backward traveling waves. If the first wave comes from the line towards the bus, it's an internal fault. If it comes from the bus towards the line, it's an external fault. Once the relay confirms the fault is internal and in its own zone of protection, it sends a trip signal to the circuit breaker. Because it only needs the very first wave front to make this decision, it can issue a trip command in a fraction of millisecond, drastically reducing the equipment damage and improving the power system stability. So this is the working of traveling wave fault relay.